Right, you know, videos, really, and that was like. You read no of us, and then, oh yeah, I was read out. I think they did it. Like, oh, I'm not supposed to look at it. Yeah. I show it. I was just right now.
Okay, good morning. Let's go ahead and get started. We're gonna change directions a little bit today, and we're gonna start talking about this new idea of voltage that's very much connected to the ideas that we've been developing of electric field and electric force. You remember Physics 105, right? And you remember that we got to a place in Physics 105 where we kind of divided up the class. We got to that section on energy, and suddenly on the exam, we had a lot of A's and a lot of C's. There weren't very many B's. It was just kind of a double hump distribution. And it wasn't really about how well you understood energy. It was about how well you could do algebra, because the energy problems very, very quickly, after 2 steps, turned into algebra problems. Well, it turns out that voltage is just very much related to energy. And so we're back there at that same place where if algebra is just something you feel comfortable with, this is going to be easy. And if algebra is something you don't feel comfortable with, this is going to be challenging. So, and you know which camp you're in. Let's start by talking about this page in the tutorial that you watched yesterday. Remember, there were 2 charged balls, A and B, and they were glued to the table, and they had to be insulators, plastic, ceramic, something like that. And the reason they had to be glued to the table is that we were going to bring a 3rd charge C, into the room. And what we wanted to do with that charge C was to measure that electric field due to A and B. How big is it, and what direction does it point? And we didn't want that 3rd charge, C, to change the problem. We didn't want, when we brought in that 3rd charge, C, we didn't want the charge on A and B to move. Well, first of all, if they weren't glued to the table, balls A and B could fly off the table. That would change everything. But also, if those balls were metal, we know that by bringing in another charge, the electrons can swim to some other place on the metal. And that's why it was important that these be fixed in place and non-conductors, non-metals. But then the real issue on this page was, what happens when I bring in that charge C? I mean, now there's 3 charges in the room, right? Now there's 3 charges in the room. So what's the electric field that's important? When I'm trying to look for the force on ball C, do I want to think about this electric field or this electric field? Tell your neighbor which one it is. It was one of the tutorial homework problems.
No, but I think it said, when you bring in Steve, what field do you want to look at? Yeah, you're right. You don't want, he was saying that you don't want A and T.
Okay. The answer goes back to that very first thing I told you about fields when we were talking about Captain Kirk running down that tunnel and getting thrown on his keister. Remember, I said there were 3 things that were important. The field was invisible Otherwise, Captain Kirk wouldn't have run into it. And you have experienced that. It's invisible in the sense that it's abstract. It has those waffle words. And some of you have been struggling with that. It's invisible to your minds and you're trying to find it, okay? The second thing I said was, Captain Kirk didn't make the field, that was the Klingons. And that's what we're talking about here. This electric field that is pushing on the test charge is due to all other charges except the test charge. Okay? Captain Kirk didn't make the field. That's Captain Kirk. Okay? The Klingons, all the other charges made the field. If I want to look at the force acting on charge C, it's the test charge. And so the electric field that I care about that's going to be acting or pushing on ball C is this one, okay? Ball C doesn't see that because ball C doesn't push on itself, you know? Okay, A and B are pushing on ball C. That's what ball C experiences, that right there. Well, what's this? Well, this is what would be experienced by a fourth charge, D, if it came into the room. It would be pushed by everything that's not D. It would be pushed by A, B, and C, okay? So you have to be clear about who are the Klingons and who's the Captain Kirk, okay? We're pushing on C. See if your neighbor followed that. If not, you know what to do.
This makes sense. I think it's kind of like.
What's that? Oh, what was the third thing? The third thing
See what it see itself.
was that there was no force until we put Captain Kirk in the field. And so what I mean by that is that if I have some sources, it can set up this field and it's just invisible and it's just in the room. And nothing's getting pushed until I bring ball C in there and then it gets pushed. Okay, so as soon as I bring in a test charge, the field creates the force that pushes on that test charge. Okay, that in the Captain Kirk example, the field was in that tunnel for 20 years before Captain Kirk finally came there, and then he got thrown. Okay, questions? Let's move to voltage. Now, last day I told you that it takes about 30,000 volts to throw a spark through dry air 1 centimeter. So you can imagine how many volts we had there. Now, what's causing that huge voltage, we will understand in about a month and a half when we talk about induction. But you can see that that's just hundreds of millions of volts. Now, you notice that that arc moved upward. Just tell your neighbor real quick why that was. Why did it move upward?
I don't know. I said, I'm not sure I've seen it.
Okay.
Yeah.
Once we have punched a hole through the air by ionizing a whole bunch of molecules, that becomes the easiest path. And that's the way that current is gonna flow. And as that heats up the air around it, the warm air rises, bringing the easiest path with it. And so the arc goes up like that. Okay, so let's talk about what this is. You know that it has to be connected to energy because we defined energy back in 105 as, anyone remember? The capacity to do damage, to mess things up, to break things, okay? And we had capacity to do damage because you're going fast. We had capacity to do damage because you're got a boulder high above your head. Let's talk about that boulder with this little pretest that we've got here. Who's going to help me pass these out? Thank you very much. How about someone over here? Anyone helpful? Feeling helpful? Thank you, sir. Okay, and I'll start in the back. There's plenty of seats if you want to be more comfortable. Or if you would prefer to suffer in a monk-like fashion, we can certainly arrange for that. Okay. Does everyone have one? As soon as you get your copy, go ahead and fill it out. Pretend that it's going to determine whether you get into med school or not. Did you guys get any? Oh, it stopped right there. One more. Can't do it. Not getting enough here? Those aren't needed? Okay. You guys have gone digital. I'm still from the age that used paper. We had just barely discovered it, actually. Paper. Thank you. Appreciate it. Okay, it's not critical that you finish that, it's just critical that you think about that. Let's work it together. The first thing you notice is that this boulder is clearly a prop at Disney World because it's 6 meters tall and has a mass of 10 kilograms. It's some kind of really light styrofoam, okay, so that it can be lifted. If we remember back to the day when we were talking about energy in 105, we always talked about energy buckets. That's because energy is a scalar, it's not a vector. And if we always choose the lowest point in the problem as our zero, we'll never have negative energy. I look at this formula for kinetic energy, it's got to be positive. I look at this formula for spring energy, it's got to be positive because of the square. And as long as I put the lowest point of the problem, my zero, H is always going to be positive, and so gravitational energy would be positive. So it's like paint. You got it, you don't got it. And if you got it, you can put it in a bucket. And we take the different types of energy and add them together to get something that we call total mechanical energy. Or sometimes we just call it total energy. Sometimes we just call it mechanical energy. We're careless that way. Now, if we call this our zero of height, then there's no gravitational energy and it's not moving, so there's no kinetic energy. So I've got no total energy. And then a hand, Rand, a friend of mine, takes that boulder and slowly at constant velocity moves it to the top of the cliff. Now the question is, how hard does Rand have to push? Well, if I look at a free body diagram, the weight on a 10 kilogram boulder, if we take gravity to be 10 instead of 9.8, it's just going to be 100 newtons. Now, the question is, does Rand have to push more than 100 newtons, less than 100 newtons, or equal to 100 newtons to move that at constant velocity up to the top? Tell your neighbor real quick. Yeah.
I mean, equal or.
If you believe Newton's second law, if the acceleration zero, my diagram should scream balance. And so that means the force by Rand on the boulder has to be exactly 100 newtons. Now your gut's telling you that it has to be more than 100 newtons to get it started. And it has to be less than 100 newtons to get it stopped at the top. But during the whole process, on average, he's pushing exactly 100 newtons to get it up there. And then he leaves it up there at rest. Okay, so if I look at the work done, and we call it werk, those of you that didn't have 105 from me, I call it werk because it's very different from what you did on the farm, okay? The werk is going to be positive because Rand is pushing in the same direction that it's going. And from our definition of werk, that gives me positive werk. And if I multiply the 100 newtons by the 12 meters, I get 1,200 joules. And what bucket does that go into? Well, if Rand puts it up there at rest, there's nothing in the kinetic energy bucket. It's all in the all 1,200 joules are now in that gravitational bucket. And that tells me my formula for filling that bucket. That's how I got this formula here. I just essentially took the werk that I had to do to fill that bucket, and that's what told me the formula for the bucket. Is that coming back to you? It's all like a bad dream that you had forgotten and now it's crashing down upon you. Okay. Now, Rand, after a while, just decides to come over and kick that boulder off the edge of the cliff. Now, I'm not suggesting that that's a smart thing to do. That's a terrible thing to do. That could endanger somebody. Do not do that. But how much external Verk is being done there? Nothing. He just barely tapped it. Okay, and then he left. Very irresponsible. Okay, but the key is he did no external Verk, and so that means the total energy is still 1,200 joules. But where is it now when it gets to the bottom of the cliff? It's in the kinetic energy bucket. So we're going to see this over and over and over again during the next week. This is going to be the one problem that we keep solving over and over again because it's a very important physics problem. If I want to know how much kinetic energy I have at the bottom of the cliff, I need to know how much potential energy I had at the top of the cliff. Because in the falling, there was no external Verk done. We just sloshed the energy from one bucket to the other. Okay, well, that wasn't electricity. So let's talk about electricity. What I have here are two plates, one positive and one negative. And we know from last day that this is a very useful situation, configuration, because it gives me a uniform electric field in between the plates. Now I'm going to take you back a little bit. Next to this cliff, I've got a uniform gravitational field. It's 9.8, we're going to call it 10, down everywhere. Okay? And this boulder doesn't want to be up there. It wants to be down at the bottom of the cliff. That's its happy place, right? And so when given a chance, it races to its happy place. And Rand had to do positive Verk to get it away from its happy place, to get it to the top of the cliff. As Rand was pushing that up to the top of the cliff, it was like he was cocking a gravitational spring, storing energy. And that's why we call it potential energy. It's potentially can be released a little bit later. Okay, well, now let's fast forward. And I want you to look at this problem, this situation, like this. Okay, everywhere in there, I've got the same electric field, it's uniform. Everywhere in there. And so you can think of this as the bottom of the cliff, and this is the top of the cliff. And this is like the gravitational field, only it's the electric field. And if I take a positive 1 Coulomb, okay, I reach into my pocket, I pull out 1 Coulomb. That 1 Coulomb wants to be at the bottom of the cliff. It wants to be next to this negative plate. It doesn't want to be next to that positive plate. Does that make sense? Okay. And so if I move that Coulomb all the way from A to B, I'm going to have to do positive Verk, just like Rand had to do positive Verk to lift the boulder. Okay, only this time I'm fighting against an electric field, whereas Rand was fighting against a gravitational field. But it's the same thing. I'm storing energy. In this case, as I move that charge from A to B, I'm cocking an electric spring, whereas Rand was cocking a gravitational spring. But in both cases, we're storing energy. Okay, so I move that over to B and I store energy. Now, this formula, the Grant-High Verk energy formula, we used over and over again in 105. And the way we read this was that the energy in the morning was always equal to the energy at night, except when it wasn't, and it usually wasn't. Okay, whenever we had external Verk, we changed the energy. If we did positive Verk, this was bigger than that. We did negative Verk, this was smaller. But often, and in this part of our class, always, we don't really care about the initial energy or the final energy. We care about the change in energy. So I can rewrite this equation as Verk external is equal to energy final minus energy initial, which is anytime we have a final minus initial anything, that's a change. And this is a little bit of a problem. That E doesn't stand for electric field. I apologize that energy and electric field start with the same letter, but that's not really on me, okay? I didn't name them, okay? But you know from context when we're talking about energy and when we're talking about electric field. How do you know? Because I use a blue pen for electric field, right? Okay, now, suppose you wanted to know what the change in your net worth was. And in your bank, you had 3 bank accounts. Okay, you had a checking account, a savings account, and a CD account. Well, what you would do is you would look at the change in the checking account and the change in the savings account and the change in the CD account, okay? Likewise, Verk can change the total energy, and it can either change the kinetic energy bucket or the gravitational energy bucket or a new bucket we're going to call the electric potential energy. Electric potential energy. Now, in this case, we're dealing with something very, very light, very small mass. And so, and we're going horizontally so that there would be no change in gravitational energy. And folks, the problems we're going to be working in the next week and a half are going to involve protons and electrons with masses so tiny that the gravitational energy is just negligible. And so what we're going to be doing is, we don't care about that. We're going to have this formula up here. And what we say is that any Verk that's done can either change the electric potential energy, or it could change the kinetic energy, or it could change both. But we're going to move this charge in a very special way. We're going to start it from rest. We're going to move it slowly to B, and we're going to stop. And we're going to do that so that the change in kinetic energy is 0. Why do we do that? Because I need a formula to fill that electric potential energy bucket. Just like I derived a formula on how to fill this gravitational potential energy bucket. I devised a system where I was putting energy into the system, but all of that energy went into one bucket. In this case, the electric potential energy, cocking the electric spring, okay? Now, suppose, I'm making this up, suppose I had to do 100 joules of Verk to get that 1 coulomb from A to B. Can you accept that number I just made up? Okay, now, answer this. What if the test charge I was moving from A to B wasn't 1 coulomb? What if it was 2 coulombs? How much Verk would I have to do to move that from A to B? Tell your neighbor real quick. It's obvious. What is it? Okay. I hope in your head you're screaming 200. 200. Because if it's 2 coulombs instead of 1 coulomb, you're going to have to fight an electric force that's twice as big for the same distance. So you're going to have to do twice as much Verk, okay? 200 joules. Now, the change in electric potential energy is now 200 joules. Well, let's go further. What if the test charge was 5 coulombs? Shout it out. 500. What if it was 10 coulombs? 1,000. What, oh, this one's different. What if it's -1? What if it's -1 Coulomb? Now think about it. I wanna start from rest. I wanna move it at a slow, constant velocity to B and stop. But if I had a -1 Coulomb, does it wanna be here at the bottom of the cliff?
No.
No, it doesn't wanna be next to this negative plate. It wants to race over there. It wants to race over there faster and faster. So if I wanna bring that from A to B, I've gotta push on it this way while I move it that way. What kind of arc am I doing? Negative arc. And I'm doing -100 joules of air. Now, I hope you see a pattern. I hope you're seeing that there's an easy way to write this in general. And that is, I just take the 100 joules for each Coulomb. That's what it took for a +1 Coulomb. And then I just scale it by how many coulombs I was actually moving from A to B. Okay? Now, this amount of Verk that I had to do to bring 1 Coulomb across, we give a name to. We call that the change in voltage from A to B. Okay, that is the electric voltage. Now, at this point, I feel a need to apologize to you for mistakes that have been made by those in my profession over a lot of years. We get really, really sloppy when we talk about voltage. In many textbooks and in many classes, indeed on this campus, I've encountered it a lot. People refer to voltage as potential. But my experience over 4 decades has been that potential sounds a whole lot like potential energy. And if I call voltage potential, my students get confused. And so I swore a blood oath with my friend Jeff Adams that I would never, ever call it potential. It's just always going to be voltage. And indeed, we only ever really care about voltage difference. And so if I'm really being careful, I'll always talk about the change in voltage from A to B. Sometimes I get careless and just talk about the voltage from A to B. But what I mean is the voltage difference from A to B. Okay? Now, what does that mean to say that there's 120 volts at this wall from that hole to that hole? What does that mean that there's 120 volts? Well, first of all, you know that you should be afraid. You've been taught by your parents not to stick things in there, okay? The bigger the voltage, the scarier it should seem to you, okay? And that's because voltage, as you can see, is an energy. And energy is the capacity to break things, to mess things up, to do damage, okay? And the more energy you've got there, the more damage. Now, voltage is not energy, this is energy. Electric potential energy. Voltage is energy for each Coulomb, okay? As current goes through the wires, okay, what we're doing is giving energy to each 1 Coulomb, 120 joules if it's 120 volt outlet there. See if your neighbor just followed what happened. Do a buddy check. Do a quick buddy check.
Energy, voltage is energy, but like it's dependent on. Yes. So that's
Now-
why you multiply it by.
This is how we define electric voltage. In truth, electric voltage difference. The change in voltage from A to B, there's 2 ways to think of it. One is it's the change in potential energy if I bring 1 Coulomb charge from A to B. Now that comes from this definition up here. if you set the test charge equal to 1, then the voltage difference from A to B is just the energy storage from A to B. How much energy was stored when I cocked the electric spring? Okay, now, because we were moving that charge from A at rest to B at rest, we weren't changing any of the kinetic energy. We were getting rid of this. And so another way of looking at it is just how much Vert I would have to do as an external agent to move that test charge 1 coulomb from A to B. But in a very specific way, from rest to rest. Okay? Questions? Okay. Now I hope that everyone's seen so far that joules for each coulomb is commonly called a volt. Okay? So which point, A or B, is at the higher electric voltage? Let's do that with our clicker. We haven't had a chance to use our clicker yet. So if you think A is at the higher voltage, you just click your button A, and if you think B is at the higher voltage, click B, and if you're not sure, click C. Okay. Okay, last call. Get your vote in. Get your attendance points. Okay, good. B is the right answer. And it's definitely not E. Okay. Now, how do I know that? Because I'm moving a +1 coulomb and I'm fighting this electric field. So I'm pushing in the same direction I'm going. I'm doing positive Vert. When I'm doing positive Vert, I'm putting energy into the system. So I got more electric potential energy at B than I've got at A. So this is what the voltage looks like in there. If it were a gravitational problem, this would be the top of the cliff, and this would be the bottom of the cliff. Okay? Now, how does a positive charge want to move? Well, if I put a proton at B, it'd want to race away from this positive plate. But another way of thinking of it is that it wants to race in the same direction as the electric field. A proton is a positive charge. If I take a field that's to the right and multiply it by a positive number, I get a force to the right. That's going to speed it up to the right. And so that means that positive charges, like protons, move downhill. They move from the high voltage to the low voltage. Now, when I say the change in voltage from A to B is 100 joules for each coulomb, another way of saying that is that it's plus 100 volts. A volt is just a fancy way of saying joules for each coulomb in order to honor a dead professor. Not a bad thing to do. Now, if I were to tell you that the voltage of B is 600 volts, you could immediately tell me what the voltage at A is. Well, the change from A to B is a plus 100, so this must be 500 volts. But if A is 800 volts, B has to be 900 volts. And I don't care which of those is true, because it's arbitrary. It depends on where you set your zero of height. In the same way that it's arbitrary for where we choose our zero of height in a gravitational problem. Okay, sometimes we set zero of height at sea level, in which case we're up at what, 4,000 or 5,000 feet here. I'm new to town. okay, something like that. If we choose Main Street Provo as our zero, then, you know, right now we're good 30 feet up. Okay, but what matters, if I drop something, is just the change in elevation, not what I was calling my zero. Does that make sense? Likewise, we very rarely care about the actual number at any one point. We only care about the change in voltage. Now, in the whole grand universe, there's really only one voltage problem. If you remember me saying this back in 105, there's really only one force problem, and we keep on dressing it up different so that it looks like a new problem, but we just keep doing the same thing. We draw a free body diagram, we use Newton's second law twice. The same thing's true here. There is only one voltage problem, and this is it. We're going to solve the one voltage problem that you're going to see over and over again on your homework and on the next midterm. So let's do it. A proton is released from point B and it goes racing off to point A. And the question is, how fast is it going when it gets to A? This is like dropping the boulder from the top of the cliff and asking how fast is it going when it gets to the bottom of the cliff. Your gut knows what to do. You figure out how much potential energy it had, and you turn that into kinetic energy. Is that what you did with the boulder? Yeah, let's do it now with this. Bearing in mind that we know the mass of a proton, that's something that you've memorized in what, third grade, you've known that? Okay, and we know the elementary charge on a proton. We've known that for weeks. Okay, so first of all, the proton isn't going from A to B. It's going from B to A. So if the change in voltage from A to B is plus 100 volts, what is it going the other way?
Negative.
Minus 100 volts, okay? Now, what we care about is the change in electric potential energy. The voltage change is just a way of getting it. It's like that price of a 1 gallon of gas. If I know how much energy got stored for 1 coulomb, I know how much energy got stored for any amount of charge, okay? So if I take my test charge of 1.6 times 10 to the minus 19, and I multiply it by negative 100, I get a negative number. What does the negative number mean when I'm talking about a change? Tell your neighbor real quick. Minus signs get in our way. What does it mean when I'm talking about a change? I hope you said losing. I'm losing energy. I'm losing electric potential energy. If your bank account had a negative change, you'd know what that meant. You're losing, okay? So anytime you've got a change, a delta that's negative, think of a bucket that's draining out, okay? So what happens to the kinetic energy? Well, if I just let that proton go at B, that's like Rand kicking the rock at the top of the cliff. No Verk is being done. No external agent is doing Verk. We just let it go. And so that means the energy has to stay the same, the total energy. And that means whatever is lost in this bucket is going to show up in this bucket. Okay, so let's go back to this equation here. I'm going to write this EPE, okay? In the vast majority of the problems that we're going to be solving, it's a small proton or an electron, and you can't reach in with your hand and do Verk on that. You just can't grab a proton. And so this is going to be 0. When you release a proton or release an electron, that's 0. And so that means whatever this is, this has to be the same but at the opposite sign. In other words, the change in kinetic energy is always going to be minus the change in electric potential energy. And that's going to be your starting point in 99% of your problems. And I want you to see this visual every time you use that equation. In order to get this bucket to fill up, this bucket has to empty. Okay? Now, what we found was that the electric potential energy was emptying, right? I had that minus sign saying that this much energy was lost in the electric potential energy bucket. And so that means that much energy must have showed up in the kinetic energy bucket. And I started from rest. It was released from rest, so it had nothing in the bucket to start with. So the change in energy has to be the final energy if I started from zero. Now, I know that energy, kinetic energy, is 1/2 mv squared. If I plug in the mass of the electron, I'm sorry, proton, I didn't mean to say electron, I can find a speed that no one really cares about. It's the process that we care about. But know that that's darn fast. That's really very fast. Okay? See if your neighbor followed that one voltage problem in the universe.
Like I made it repeat later. I don't know that part where he said that the energy. Oh, yeah. Negative. He was saying that.
Okay,
Just. It's kind of a positive.
again, I want to drive this home. Voltage is just the change in potential energy if I were to bring 1 coulomb from A to B. And if I do it in a very clever way, namely from rest to rest, it's also equal to the amount of work I would have to do to cock that electric spring. Now, let me try to make this visual for you. That's a younger Greg, a much younger Greg. That bowling ball has a capacity to do damage, but not much, not where it's at there. I would say it has a low gravitational potential energy. Likewise, if I put a positive charge here, I would say that has a low electric potential energy. Both the bowling ball and the positive charge are at the bottom of the cliff, so to speak. Okay. Now, if we do positive work on the bowling ball and do positive work on the positive charge, we're storing energy. Here we're storing gravitational potential energy. Here we're storing electric potential energy. And when we get the bowling ball up there, it is at a higher gravitational potential energy. And we say that our change in potential energy during the process was positive, like your bank account getting fuller, okay? Likewise, when we get that positive charge up next to the positive plate, we say that it's at a higher electric potential energy. And we say that the change in electric potential energy was positive. Now, if we let the bowling ball go and we let the charge go, well, what happened? What happens? Yeah, the potential energy, whether it's gravitational potential energy or whether it's electric potential energy, turns into kinetic energy. Okay? And that's what we always care about. You know, if I accelerate this electron through 1,000 volts, how fast is it going to be going? That's what they worry about when they're at a particle accelerator, when they're trying to split atoms or do something like that. Okay? Now, where does that kinetic energy come from? Again, when you go to sleep at night, I want this slide to be what you see before you fall asleep. Okay, when you close your eyes, this is what I want you to see. Okay, it's a zero-sum game. The kinetic energy comes from a decrease in electric potential energy. Now, I hope that by now you've seen the same game that we played with the electric field and the electric force. The electric field was defined by this equation here. And the electric voltage is defined by this equation here. In both cases, we can get a gut level understanding of what they mean by setting the test charge equal to +1 coulomb. And in this formula, if I set that equal to 1, I get my gut level understanding of the electric field. The electric field is the force that would be acting if I put 1 coulomb there. Okay? Likewise, I can understand voltage. The electric voltage from A to B is how much change I have in my electric potential energy bucket if I move 1 coulomb from A to B. But I never do. What if I move 2 coulombs? What if I move 3 coulombs? What if I move 1.6 times 10 to the minus 19 coulombs? I just take how much energy it took to make 1 coulomb move from A to B, and I scale that by what I really brought from A to B. Okay? Is it all making sense? I want it to be real. I don't want it to just be an equation. I want it to speak to your soul so that when you leave here, you've got a new friend. Voltage. A powerful friend. Scary friend. Okay? Now, what direction is the force on an electron? Okay? If I put the electron between these plates, I know that the electric field is always going to point in the same direction as the field line. And the field lines are always going to start on the positive plate and go to the negative plate. So that electric field is always going to point towards the bottom of the cliff. But that's not the way the electron is pushed. Because if you take an electric field to the right and multiply it by a negative electron, I get a force to the left. Okay? Now, the question is, which point now, A or B, is at the higher electric voltage? So with your clicker, tell me what you believe. Now you can click. Okay, last call. Get it done. Whoa. Bazinga. I gotcha. I gotcha. The answer is not A. Okay, the answer is B. Remember the waffle words, people. Okay, just like the electric field doesn't depend on the test charge, the voltage doesn't depend on the test charge that you're taking from A to B. Okay, the voltage is always going to be higher near the positive plate and always lower near the negative plate because of those waffle words. The voltage is how much work I would have to do to bring +1 coulomb from A to B. Well, I'm bringing a negative charge from A to B, Greg. I don't care. That's not what the voltage is about. The voltage is about what I would have to do if I reached into my pocket and if I pulled out 1 coulomb. So the voltage always stays the same, independent of what you're moving from A to B. And that's a good thing, people. That's something you should be thankful for, not confused by. Okay? So how does a negative charge want to move? Uphill. Okay? They want to move uphill. Now, back in the day in 105, life was easy. we only had one flavor of mass. All boulders were positive, and all boulders went from the top of the cliff to the bottom of the cliff. Well, it's a brand new day, okay? Now we got two flavors of charge, and they go the other way. But it would be useful to have something that we could count on always being the same. And so let me suggest that we redefine what we mean by down, okay? If I look at the gravitational case, I have a gravitational field that always goes from the high elevation to the low elevation. Always, 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 okay? And my only one flavor of mass always is going to speed up in that direction, okay? Now, during that process, was the change in kinetic energy positive or negative? Shout it out. Positive. Was the change in gravitational potential energy positive or negative? Shout it out. Negative. And the change in elevation? Negative. Okay. Now, let's look at the electric case. Suppose I had a region here that was at 250 volts, and here a region that's at 150 volts. The electric field always, 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 every stinking time goes from the high voltage to the low voltage, okay? Just like gravitational field goes from high elevation to low elevation. Always, always. But if I release a positive charge, it's going to race in the same direction as the electric field. It's going to go from high voltage to low voltage. Now, again, let me ask you these questions. Change in kinetic energy, positive or negative? Positive. Change in electric potential energy, positive or negative? Change in voltage? It went from 250 to 150. If your bank account went from $250 to 150, what would that be? That's negative. Okay. Now, let's look at the case that's different. If I take a negative charge, it's going to speed up in the opposite direction. The change in kinetic energy, it's speeding up, that's still positive. The change in electric potential energy, well, that kinetic energy has to come from somewhere, right? So this has to be negative, but the change in voltage going from 150 to 250 is positive. And that's the problem. That's where things fall apart. So if we redefine what we mean by down, if we redefine down, and physicists do this, to mean to a lower potential energy, everything goes to a lower potential energy. Everything falls to a lower potential energy. Now, how would I get these regions of high voltage and low voltage? Well, with plates. A positive plate up there and a negative plate there. It's always going to be a higher voltage near the positive plate and a lower voltage near the negative plate. Okay? Check on your neighbor. Wake them up if you need to.
Like I get that it's gonna go, something is gonna go up.
I think you're on.
Because that's just how the chart. But I don't understand how that's going from higher.
We haven't fun yet, Oliver.
Potential better. Because, you know, so you're, as you.
Okay, are there questions that I can answer? Let's help you with your homework. Okay? This is the first problem on homework set 5-1. Point A is at an electric voltage of 750 volts. Point B is at an electric voltage of 950 volts. An electron is observed moving at some speed at point A. We don't know what it is. But when it gets to point B, is that electron going faster, slower, or the same speed that it had at A? Let's again use our clickers. Okay, get your vote in. Last call. Good. The answer is A. Good. Okay. So let's solve that. Well, first of all, let's look at the voltage. If I'm going from 750 volts at point A to 950 volts at point B, again, if that was your bank account, you'd say that's a positive change, okay? But the voltage change is just a step in finding what I really care about. What I really care about is the electric potential energy. And you remember that the electric potential energy is the voltage change scaled by the test charge. Well, if the voltage difference is positive and it's an electron, so this is negative, if I multiply a negative by a positive, that makes this negative, okay? And if my electric potential energy bucket is draining, my kinetic energy bucket is going to be filling. And so I have to speed up. And that comes from this equation here. If this is a -6, that minus sign there is going to make this a +6. Since it all has to add up to 0, if this is going to be positive, that has to be negative, okay? By the same amount. Okay? Oh, one of your homework problems is done. Okay. Now, one of the most useful equations that's going to be in your toolbox come that exam is just brutally simple. Okay? And I call it the ED equation. And let me just show you what it comes and where it comes from. Let's say that I have to do a certain amount of Verk from A to B on 1 coulomb. Okay? So the voltage is from A to B is going to be a certain amount, I don't know, 300 volts, whatever. Now, if I were to double the field strength between A and B, how would that affect the voltage between A and B? Tell your neighbor real quick. Okay, I hope it was obvious to you that now I'm fighting an electric field that's twice as strong. I got to push twice as hard for the same distance. I got to do twice as much Verk. Well, what if we go back to the original field and instead of having A and B that far apart, we move them halfway as far apart? What does that do to the voltage between them? And when I say voltage, what you should be thinking is the amount of work I have to do to bring 1 coulomb from A to B. What happened to that when I moved them closer? It got smaller by half. It got smaller by half. So this voltage between two plates where the electric field is uniform depends on the electric field strength, and it depends on the distance between A and B. But how does it depend on electric field and the distance? Okay, how do we find the formula for the change in voltage given an E and given a D? Well, let's use the formula that we started with, that Verk is what changes energy. And if we move things from rest to rest, we can get rid of this term right here. Okay, so we're going to start with a charge and we're going to move it from A to B, starting from rest and ending at rest. So there's no change in kinetic energy. Now, that gives me this. I just replaced the change in electric potential energy with the test charge times the change in voltage. And that's what I'm looking for. Now, if I do a free body diagram, I have two forces on that test charge. I have the electric force, which is just the test charge times the electric field. And if I want to move that at a slow, constant velocity, I have that external force, which is going to be the same size. And so if I plug that in for the external force, and then I cancel out the test charge on both sides of the equal sign, I get a formula that I call the Ed equation, okay? Now, caution. This formula is so simple, so elegant, that you're going to be tempted to use it in every situation. But it has caution tape around it. You can only use it when the electric field is uniform. And that's going to be between charge plates or near a single charge plate. It's whenever those field lines are parallel. Now, I want you to listen to this and tell me whose voice it is.
You're getting it right from the horse's mouth.
Who is that? You people are so young. Mr. Ed. You never saw this show?
Hello, I'm Mr. Ed.
A horse is a horse, of course, of course. You never saw that? Wilbur can talk to Mr. Ed, and Mr. Ed can talk back. And the way they did this is they shoved a whole bunch of peanut butter in Mr. Ed's mouth, and the whole time he's trying to get it out, and it looked like he's talking, and they put words in his mouth. It would be considered cruelty to animals today that never get away with it. But when one of my daughter-in-laws asked what I wanted her to call me now that she was a member of the family, I said Wilbur, and she still calls me Wilbur. Okay. Okay, so if I take two plates here and I hook them to a battery, say a 12-volt battery, the positive terminal to one and the negative terminal to another, I set up an electric field between those plates. And by moving the plates closer to each other, I change that electric field. Do I make it weaker or stronger by putting them closer together? Tell your neighbor real quick. Okay. Now, here I've asked you, what is the electric field between the plates? And you know that, well, first of all, let me tell you, the job of a battery, and we'll understand this on Tuesday, the job of a battery is to keep the voltage difference between the negative plate and the positive plate at the same voltage as the battery terminals, okay? That's what batteries do, okay? So the voltage from A to B would be 12 volts. Now, I asked what's the electric field between the plates, because the electric field is going to be the same everywhere between those plates. It doesn't matter where I look between those plates. But that's not the way I'm going to ask it on the midterm, people. No, because I'm evil. I'm going to say, what's the electric field exactly in the middle of the plate? Or I could say, what is the electric field 1 millimeter from the negative plate, or 1 centimeter from the positive plate? And you're going to have to say, oh, nice try, Francis, but I know better. The electric field's the same everywhere. And I can find that electric field strength from the Ed equation, okay? Now, what I've done here is I've purposely written the Ed equation in a very careless form. If you write the Ed equation this way, I'm going to trip you up on that exam, okay? The way you want to write that Ed equation is that the change in voltage from A to B is equal to the electric field times the distance from A to B. These indices should always be the same as those indices. And you'll see in some of the homework problems where if you're not careful with that, you'll get tripped up. You'll get tripped up. And so in this case, if I take the voltage of 12 volts and divide it by the distance, in this case, we made D equal to 1 centimeter or 0.01 meter, I get an answer of 1,200 newtons per each coulomb. Now, wait a minute, Greg. If I take 12 volts and divide by 0.01 meter, I get 1,200, that I see. But I don't get newtons per coulomb, I get volts per meter. Okay? But that's the same thing. Remember, a volt is just a joule for each coulomb. And I've got to have that meter in there in the basement. And I remember that a joule is just a Newton times a meter. And then I cancel out the meters and I get newtons for each coulomb. So I can write an electric field either as volts per meter or newtons for each coulomb. Now, in this case, I have the voltage in two different regions. We still have a couple of minutes, that's all it'll take. And if I were to ask you, which direction does the electric field point in region 1, your gut should scream, always from high voltage to low voltage. Just like the gravitational field goes from high elevation to low elevation. In region 2, also high voltage to low voltage. Now, that's the easy part. What if I asked you in which region is the electric field going to be strongest? Okay. In which region is the electric field going to be strongest? Remembering that I can think of electric field as volts for each meter. Okay. What I would do is I would pick 2 points, A and B, arbitrarily, and I would see that in region 1, my difference in voltage from A to B is 60 volts. In region 2, over the same distance, I would have a change in voltage of 120 volts. I have a bigger change in voltage per meter. And so the electric field would be twice the size in region 2. Now, folks, I know that was a lot. I know that that was a whole lot of information to put into you in one 75-minute period. You hurt right now. You ache right now.
Yeah.
On Tuesday, we'll do it all again and make you ache again. You're welcome. Have a good weekend.
Hi, there's greater. Oh, I was like, what do you mean?